Yeah, so this is a project I did during my honors, which was 2 years ago. So my memory might be fuzzy, but hopefully, in the past 2 weeks, trying to look at it again. Um, I can give you guys a good overview, and you'll find something interesting out of this. So what I learned in well in the project is basically the structure of the donor qubit device and some quantum error correction, specifically to improve control fidelity by tracking the gyromagnetic ratio of the qubit. So here's the device they use in so in the group in UNSW. So this is the donor qubit device, which is just it's very similar to the MOS transistor. It's just slightly modified. So you have the aluminum gate on top with the silicon oxide dielectric in the middle, which is which acts as the SET island. SET being the single electron transistor, and the bottom is the pure silicon semiconductor. So practically what we're looking at is I mean, it looks like a bunch of wires, but it's quite simple if you break it down. I don't know if you see my cursor.
No, I can't.
Yeah, the laser pointer.
Yeah.
Okay. So with the silicon, I think the silicon oxide is broken down to three parts by the barrier gates, which is the left barrier gate and right barrier gate. It's separated into source, SET island, and drain. And with this, we can control the current flow between the source and drain by shifting the electrochemical potential of the SET island. And here are the phosphorus atoms and sitting on top of plunger gates. So the phosphorus atoms are the qubit. They hold the qubit electrons. So they're kind of like a hydrogen potential well, which works very well with electron, I guess, with the coherence time. So you have the bias, source image bias, and then the voltage for the left and right barrier gates. And you have the top gate, which controls the Fermi level of this whole thing. Okay. Which shifts the SET island, the chemical potential of the SET island. And then you have the plunger gate, which also shifts the electrochemical potential of the SET, but also it influences nearby electron traps, including the donor qubits here. So additionally, you have the static magnetic field along Z axis of the qubits, which creates the Zeeman splitting. And then you have the oscillating magnetic field on the XY, which gives you the Rabi driving between spin up and spin down.
So the magnetic field is an external source that provides it?
Yeah. And yeah, it's just
where's that on the diagram, the magnetic field?
Oh, it's just it's outside. You're looking at here, you're looking at the chip, and looking at mostly just the gates and the voltages, and these two things are separate, kind of.
I think I'm asking because is it quite large, or is it like small, the magnetic field, like the device for that?
I'm not sure. I only know that the static field is around 1 Tesla, and I think the oscillating field is maybe even smaller than this, but yeah.
So a Tesla's quite large, isn't it? A Tesla's quite quite a bit. Is a coil? Is that right for the magnetic field, or?
Probably. I actually don't know the physical device of like how they implement it in magnetic fields. So yeah. Okay. So with the source, SCT island and the drain, you have the two barrier gates creating these two barriers here, and then you can control the electrochemical potentials of the three sections, so that you can control if you want the current to be switched on and off on the SCT island. So if there's a level, so the SCT island basically provides a platform for an electron to hop from source and then into drain, as long as it's within this source drain bias, if this platform. And if it's out, there's no platform within this source drain bias, then there's no current flowing through the SCT. And we'll see later with this, we can do spin-dependent tunneling and doing spin readouts, and so here we look at how the spin-dependent tunneling works. So here we can shift the qubit. So this is done by Zeeman splitting, and we can control how where the position of this relative to the SCT island and the drain by the plunger gate with the plunger voltage. And here we set it so that the spin up can tunnel out, or an electron can tunnel into the spin up state, which eventually relaxes down to down state. So usually when we say initialization, we initialize it into a down state. So the readout works as if you have a spin up, you can tunnel out into the electron can tunnel out into the SCT island, and you have an empty state in the qubit. But if you have a spin down, and if you set it to this position, nothing is going to happen. And what you get from the spin up with the electron and the qubit emptying itself is that you get so when the electron tunnels out and the qubit is empty, the SCT current is switched on because that's of the way we set up the device. And over some time, an electron finds its way back into the qubit, then the current switched off, and that's why you get a current pulse. Where you see a current pulse if a spin out is being read out, and there's no pulse if it's a spin down. And we can find, so there are actually several, there's a lot of electron traps around the donor, I guess, like the qubit, because the qubit is located very close to the silicon oxide layer, which is the SCT island, and there are many electron traps around it. So so that's when you see these breaks, which I'll explain in a bit. So this graph is obtained by scanning through the plunger gate and the top gate. So the top voltage and the plunger voltage. Again, they shift the chemical potential of the SCT island in a counteracting way, so that you get this straight. So these are current peaks. As you remember, if you shift the chemical potential within the source drain bias window, you get a current. If it's outside, there's no platform, and there's no current. That's why you only get a sharp peak at these points, and it's diagonal again because they counteract each other. One thing, again, because the plunger gate ionizes, I guess, the potential traps around the donor qubit, which is also close to the SCT island. And these ionizations also shifts the chemical potential of the SET island. So when these electron hops, you get a break because the SET potential shifts. And specifically, what you see is if you actually let's talk about the breakings first. So you see a lot of breakings around here near the zero region, I guess. And we find this to be the qubit, the qubit electron, because it has a very big break, and as compared to these little breaks, which we know are the electron traps. And the way we, I guess, shift into the empty phase and the loaded phase is by simultaneously controlling the plunger voltage and the top voltage to stay along the current peak. So we go from ionized donor qubit, which is empty, and as we move down and along, and at some point an electron will load into the donor qubit, and you see a break, and that's why it looks like that. So let's shift focus to the qubit Hamiltonian and the way we control the qubit on a Bloch sphere. So the qubit Hamiltonian is very simple, just the two-level qubit Hamiltonian. You have the static magnetic field, which gives you the Zeeman splitting. And here is the Rabi drive, and along the X, or you can put it against Y as well. So Y is, not Y, gamma. So gamma is the gyromagnetic ratio of the qubit electron, which is, I can't play this. Sorry. Oh, okay. Okay, yeah. So this is in non-rotating non-rotating frame, and you can see how the Rabi oscillation, the Rabi drive. With the Rabi drive, you can change from spin up into spin down. And to simplify this computationally, and we can also do it in rotating frame, and you can see it's a lot neater. And these are on resonant driving. Sorry, let me just pause these. So again, with this, it stays along the ZY plane perfectly, because it's on resonant. So the omega drive equals to omega O, which is the resonant frequency determined by the Zeeman splitting. And we have the Rabi frequency is determined by the oscillating magnetic field. And the pulse duration applied is also determined by the Rabi frequency. And all of this, you can see that the gyromagnetic ratio is an important parameter to keep track of in order to have coherent driving and control of the qubit. Okay. So the full Hamiltonian, so the idea is to have a separate qubit to the signal qubit, which we could call a spectator or an auxiliary qubit, to detect the noise. In this example, is to detect the noise in the gyromagnetic ratio, and you can feed back that information into the signal for higher control fidelity. So the way I simulated this is the two qubits are uncoupled, but I simulated in as a product state, just in case in the future I could just add in some coupled interactions, and I had to do some general rotating wave stuff as shown as this, to make it in the rotating wave and simplify the simulation. So in terms of the charge noise and what kind of noise you get from the gyromagnetic ratio, one of the noises is the charge trap noise around the silicon oxide surface. So you can think of this as a rectangular wave, as in the noise of this gyromagnetic ratio, because if you think of one single electron that is prominent and is close to the SET island, actually not the SET island, close to the donor qubit, the electron, which influences the gyromagnetic ratio. If it's hopping back and forth with some probability, you can see how it does a rectangular wave on the gyromagnetic ratio. And we need to keep track of keep track of the gyromagnetic ratio for high control fidelity because of the resonant frequency and also the pulse duration of the Rabi drive. To measure how much we're off our resonant frequency, we can use this thing called Ramsey sequence, which involves a ℧2 pulse, and then you do a wave, and then you do another ℧2 pulse. But so basically, if the driving is less than the actual driving frequency, you actually, if your estimation of the gyromagnetic ratio is less than the actual one, you're more likely to measure a spin down. And if your estimation is larger, then you're more likely to get a spin up. So this is basically mapping the off resonance to measurement in the x-axis to z-axis, by making use of the delays and the advancements in the mismatched driving frequency. So the mapping looks something like this, with 0 being 0% error. So you can see how along this line, it's quite linear. So if we measure, for example, more likely to be spin up, we can just decrease the resonant frequency, our driving frequency. And if it's the other way around, we increase our driving frequency. But there are other ways to, I guess, calibrate the resonant frequency. This is more, so as you can see, you have to get quite close to the value in order for the Ramsey sequence to work. And the goal of using the spectator qubit and the auxiliary qubit is to have a real-time calibration of the gyromagnetic ratio. So, well, for example, if you set up an experiment of your qubit initially calibrated perfectly, it's still going to be drifted off over the course of your control sequences, because of the charge traps, I guess, the charge noise. And in order to make sure that we're on resonant throughout the control sequences, we can use the auxiliary qubit to place in close proximity to the signal qubit to correlate the noise we see in our spectator qubit and feed it back into the signal qubit. So again, we start with both. The process goes. This is a lot of words. The process goes. We start with both qubits tuned, and we feed square wave noise for the gyromagnetic ratio for both of the qubits. So for the signal qubit, we just continuously do the Rabi drive, and the auxiliary qubit, we do this loop of doing the Ramsey sequence, measuring the expectation value, and then feed that information back into the gyromagnetic ratios, and then reinitialize the downstairs and do this whole thing again and again and again. So the way I implemented how I read, I guess, calibrate with the Ramsey sequence measurements is just by a simple kind of delta modulation tracking with static step size and just steps in the direction given the expectation value. For example, if it's larger than 0.5, I step in a positive direction. And if it's smaller than 0.5, I step in a negative direction. So these are just the time evolution of the data qubit and spectator qubit. And I think the frequency of the measurement on of the feedback, I guess, on the noise information is limited by the duration of the Ramsey sequence and also the qubit initialization and readout. And I think I did the whole project on some false information. I think initially I was told to do it on I think megahertz noise, but at the end, I think near the end, they told me, oh, maybe do 300 hertz. So I didn't get too much of a good result on even when I have perfect information of the expectation value instead of single shot measurements. So I mean so as you can see how this with this engineered noise tracking and how this basic tracking method performs, it takes quite a long time to I mean, depending on the frequency of the noise you're trying to track, and obviously the speed of your qubit device with the initialization and readout. But even with I think this is this is very high. This is much higher frequency than needed. And the error I used to calculate the method I used to calculate the error is very basic. It's just to find the difference between the I guess the data qubit with noise and then data qubit without noise, and the time evolution difference. As you can see, over time, the error grows larger and larger, and it's just because it's not able to keep track of it. And yeah. So at this point of this project, I didn't have much support. It's because I was working mostly in the because I was gonna move on to look at some Bayesian tracking method, which was quite complicated to do on my own. And so I switched to a different topic, I guess a side project. I put in a lot of work because I had to write the simulation from scratch by myself. And yeah, anyway. so moving on, but there was something that's interesting was after looking at Foucault and Seth's machine learning stuff, I've been thinking about how that could be incorporated in this noise tracking kind of stuff, because this is quite similar to the cart with the stepping, I suppose. But I'll talk about that later. I'll ask about that later. So I moved on to a second topic, which is the ionization shock, which was so this was looking at the nuclear spin and how much information it loses with the readout and initialization of the qubit, the electron spin. And so here we have, there's a lot of maths in this, and I think I'm just going to skip through this very fast. And I think there's something that I made a mistake at some point, but the full solution, in order to achieve what I wanted to do with the whole 4x4 matrices, it was quite difficult. So firstly, I looked at, so this is the Hamiltonian for the full isotropic hyperfine and the anisotropic hyperfine. What I was trying to do was to find how the nuclear spin is affected by the constant measurement of the electron spin. And I started with the isotropic hyperfine, which is very simple with, if you set AZZ equals to the AXX and XAYY. So what you do is you start by steady state, and the electron and nucleus state just becomes the eigenstate of this isotropic Hamiltonian. As we trace out the electron, this will cause a change in the nucleus spin. And if we reinitialize it and doing a step one, and we do it again and again, we want to see if we look at how the spin probability of the nuclear spin changes over this number of electron spin measurements, we can find, we can experimentally find the value of the isotropic hyperfine parameters. And this is just some maths I found. And I think I want to go back to this noise tracking. So wondering, Foucault, and I have a question for Foucault and Seth. So do you think this machine learning will be a good way to?
I have a questions here as well first.
Yeah.
So first, like in your system, like if we start from 0 and you're going with the time steps like 35 microseconds. So in the start, I think, okay, it's learning your noise model and then it tracks to the actual pulse. But then why it keeps learning every time? Like if it learns first time, then it should be
No. Oh, this is not machine learning.
No, even if it's not machine learning, even like if it's just some generic model, still, like if you have already got some information from the previous, like let's say one wavelength of your system, then you can use that kind of data for the noise. Like it should not be learning again. That's what my point here.
Yeah. That's what I was trying to implement. So this is a very simple wait, again, what I did here was just a basic stepping based on the expectation value measurement out of the Ramsey sequence.
Okay.
So I'm just doing static stepping here.
Oh, okay.
Yeah, so there's no prior information used. And I think, don't you need to implement some Bayesian stuff in order to do that kind of work?
In machine learning stuff, you're saying?
No, just some generic model of, I guess,
Okay.
like varying time steps or
Mhm.
like varying, I guess, step sizes and that kind of stuff.
Okay. Okay, I get that. And
Yeah.
then your question about like the machine learning for this noise mitigation.
Yeah.
Normally, I raise a question here, like if we are using at the back end the classical machine learning model for noise mitigation in quantum system, and then at the output of the quantum, we are expecting some quantum speed up. Then normally I raise a question then how we can get that quantum speed up if the quantum system is being controlled by classical system.
But I guess what I was thinking about was mostly the benefit between, I guess, the difference between characterizing the system with some Bayesian stuff as compared to machine learning.
You can definitely use that classical machine learning models like reinforcement learning or any other like supervised or unsupervised learning models for noise mitigation. There are so many papers that exist on this one, like quantum error correction and error mitigation using classical machine learning. But normally what I discuss here is like if we want some quantum speed up at the output of your quantum model,
Yeah.
and if your quantum system is being error mitigation is being done by some classical model,
Yeah.
then how we can expect a quantum speed up from that quantum model.
Sorry, I don't understand your question. Sorry.
So let's say like you have in the middle, let's say, okay, in the middle you have a quantum model.
Yeah.
There is your classical control that is doing error mitigation for your quantum system.
Yeah.
And then here you have some output from your quantum model, and let's say some machine learning that you're doing on quantum system. And
Yeah.
we want some quantum speed up in that machine learning model, that quantum machine learning model. But then the control and the error mitigation in quantum system is being done on classical system. Then that quantum speed up will not be there.
Okay. But is it generally worth it to use machine learning? Because with the resources
there are
and
so many articles that exist on this topic,
Mm.
but so in even in Cicero, there are some people who are doing some work on this direction. In Data 61, they are working on this. So the main concept behind that is the classical machine learning model should be able to detect and estimate or predict the errors before it happens, and then it can correct it so that we can have some at the end we can have some kind of quantum advantage in the model. Otherwise, if the classical model is not that kind of efficient in detecting and predicting the errors, then for sure it's going to slow down your quantum system as well. And then it does not make any sense to use that quantum system.
Yeah. Okay.
Like if you're not getting any kind of advantage from quantum system, because that system is being controlled by some classical machine learning model for error correction,
Okay.
then it means like that quantum system is being some kind of redundancy here. You can just take it out.
Okay. I think I have to read up on it.
But yes, I mean like classical machine learning is being used for error correction in quantum models, especially for quantum chemistry problems, because like in quantum chemistry, they normally claim that quantum is being used for scalability of the chemistry problems. So that's why they like some of the chemistry problems, they are not trackable on classical systems. So even if they take more time on quantum systems, still it's worth it to use it. And then for error correction in quantum system, they use some classical system.
So is your point, if we use classical algorithm for the error correction, it's a bottleneck? And
I mean, the classical system can slow down your quantum system again, because we are controlling our quantum system by using a classical system.
So is this your sort of your own original argument, or you read it somewhere?
I actually discussed it with many people, like even with Usman. So I discussed that point with him as well, because some of his team members, they're working in this direction, like using classical machine learning model. Because I attend his weekly meetings as well, fortnight meetings.
Who is it?
Usman.
Oh, Usman, yeah.
So they were discussing some point like this using classical machine learning for error correction in quantum. So I was discussing with him the same point, like if we are using classical machine learning here, then for sure it's going to slow down your quantum system and whatever the quantum advantage that we are looking for into the quantum system. But that system is being controlled by some classical model. So it means there is no speed up there, in terms of, especially in terms of time.
Yeah.
So he said, yes, that is the bottleneck there. But we have to get some classical model that is more than efficient, like in terms of that it can predict the errors in quantum model, like very specific, very not generic, but just a very specific quantum model. And if it can predict and correct those errors, then it is worth it. Otherwise, it can be bottleneck there, especially in terms of implementation time for quantum model. If you're not looking for quantum advantage in terms of time, let's say if it's in terms of like sample efficiency of your machine learning, then it's good. Then it's fine. Then it's not a bottleneck. But if you're looking something in terms of time, fast speed up, then it's a bottleneck there.
Yeah.
So it depends on your advantage that you want from your system.
Yeah.
But
yeah, go.
Machine learning in general takes up a lot of resources, doesn't it?
It depends on your data, like how complex is that, and then based on the complexity of your data, you need, maybe sometimes you just need only single layer of neural network for your model. Maybe you need 10 layers.
Yeah.
But it depends on the complexity.
But you can incorporate prior predictions with like understanding of like the noise spectrum and incorporating that into the machine learning process.
So I mean, like it depends in these terms. Like if your noise is fixed, let's say the noise model is fixed in your quantum system, then you can do a lot of pre-training. Then you don't need to train your model again when you put it online. Like when you're using it with your real hardware or using some real application on your quantum hardware, then then probably it's not a bottleneck there. But if the noise is also changing all the time, then you have to train your model in parallel as well. So that may take a lot of time.
But it's in terms of real time, I guess control, machine learning would usually be a good way to go. You say
To control the quantum systems?
Because it just to track like this kind of noise. And,
yes. Then it's a good candidate to do that. I would say.
So was that your last slide?
Which one? This one?
I mean, are you finished? As you talk finish?
Yeah.
Okay. All right. Yeah, so I've got a couple of questions, just real basic ones.
Yeah.
Could you go back to right at the beginning? So we're actually we're looking to actually build a silicon phosphorus qubit here as well. So
like this.
No, right. Or the next one, next slide. Yeah. So I'm actually not familiar with these systems. So how's it work? So just really basically, so the qubit is inside the electron spin degree of freedom in the phosphorus atom. Is that where the qubit is?
Yeah. I mean, I think it's the outer layer of the electron.
Okay, and then in this system, the qubit controls it acts like a valve for the current. Is that how it works?
Yeah, kind of. It's so basically in the So in the depending on, so this is where you would have so this is the level you would shift this your potentials to when you're doing initialization and readout, and for empty phase and control phase you shift it differently, but I don't know if that's related. Yeah.
Right. Okay. So a couple more. Go forward a couple more slides. The one was the two wells. This one. No, the previous one.
Yeah.
So these potential wells, I'm trying to understand what the difference is. So the silicon oxide surface creates potential wells. You're saying is that what you're saying?
I think it's there might be just defects on the. I think it's the defects on the silicon oxide surface.
Okay, so these the potential wells for the electron, which is the qubit?
No. They're surrounding qubits, I think, and hopping in and out. And that's all
Surrounding qubits. I thought this was a single qubit system.
Oh no, I think this might be on the SCT island, at least, or just in the silicon. I didn't go too deep into the materials side of things when I did the project, but this is what I was told. That's how it works.
What's the significance of this slide? Like what's the point of talking about this? I never understood this part.
It's so that to justify the rectangular wave, I guess. I actually have a paper on I could find a paper when they talk about like where the charge noise comes from.
What rectangular wave are you referring to?
As in, over time, if a single, I mean, the multiple, probably a lot of traps are surrounding the qubit, but if there's a single one hopping between the two wells, then you can kind of see it as the noise on the gyro-Maclaurin ratio is a rectangular wave.
Right. Oh, okay. So somehow these potential wells introduce noise into the system, which can be modeled as rectangular waves.
Yes.
And that's underpinned by a double well system or something. Is that?
Yeah. I mean, this is a very simple way to model like what's going on. I mean, there's probably multiple ones, and you can the electrons can hop in and out.
So you're saying if the neighboring there were no neighboring wells, then this noise would be completely gone. Is that correct? It's on charge.
I guess so. But there are defects in the chip that makes this. Yeah, I don't think this is avoidable. But again, this is just because it's a very established thing because they use the MOS transistor. It's very slightly modified, so you can find papers on this type of noise.
Right. So it's the whole point. There's a whole novelty in the phosphorus silicon qubit is the phosphorus atom. Is that what's like? So they have just a normal MOSFET and they dope it with phosphorus atoms. Is that what the?
I think the novelty is in using very like a pre-existing fabrication method with the MOS transistors and very because the device is very well studied. You know like the noise with the device very well. But I think one of the problems. So I talked to the quantum dot guys. So Andrea is mostly the team that does the donor Qubit stuff, and Andrew Zurak, they do the quantum dots. And when I was talking to the quantum dot guys, I think when they fabricate this, like the donor device is actually very probabilistic. I think they inject like just shoot these fast phosphorus atom into it and hopefully hopes that it lands on a good spot. I think
So
that's
without the phosphorus atom, is this just a normal MOSFET? Is this a normal transistor? Is that, or is this a special transistor?
I think so. I think it's very. I mean, maybe there's some modification with the because the SET atom. I don't know enough the structure of like the normal MOSFET compared to this.
Right, and is the point that they put the phosphorus atom in so that they can somehow control the current flow with this qubit?
Yeah, and
which doesn't exist in a normal transistor. Is that
yes,
the whole point?
yes, and phosphorus atoms is a very sharp potential well, so when you can really trap an electron.
Right.
Yeah.
Oh, okay. No. Any questions?
I just have a comment, like the thing that you were discussing about machine learning for error mitigation.
Yeah.
So there was some, maybe not recent, but probably like not too old paper on recurrent neural networks for error mitigation in quantum systems. So that can be a good candidate because like the pulse that you are showing, it's a time series data. So recurrent neural network can be a good candidate to solve that one because it also because it is also used for time series data.
Okay.
So we can try that.
Yeah, could you send me some of the
Sure,
keywords?
I can find something on that. Because that paper was basically on coherence time of qubits, probably. Not majorly on error mitigation, but they were majorly focusing on to enhance the coherence time of the qubits.
Yeah. So are they using like a, what's that called? Anyway, I'll look into it.
Yeah, I will try to find that paper and we can look into that together.
Yes, please. Thank you.
Sure. No problem.
Sure. While you're on this slide, so this is. This is engineered noise tracking.
Yeah.
What do you mean by that? What does that mean?
Engineered noise, as in the square wave. You can actually physically implement these this square wave noise on the device. So we're using a simple square wave in the simulation just to test like how well a basic method will be able to perform and how well the error rates comes out. But in the actual,
So the blue line is the noise you're introducing into the system.
Yeah, and the orange line is trying to track, I guess.
Right.
Yeah.
Oh, I see.
And you are trying to predict the blue line, right?
Yeah, not
That
but
kind of way.
in our method in our method in my honors project, we didn't really try to predict it. we just measure again, we just try to measure how much of resonant it is. So with this Ramsey sequence, we map the resonance to this linear region, and we just do a time step. So we do a step down if it's on the left side, and let's do a step up if it's on the right side, like in terms of the measurement.
So that plot with the blue line and the orange step, is that simulation or is that like actual measurements?
No, this is simulation. But you can do this. You can induce this square wave noise in the actual system.
Right.
I think you just put like parallel plates.
Right. So if you're doing an experiment, you would drive the blue line into pretend it's noise.
Yeah.
And then the orange line. How would you get that? You need to do a readout and then.
Yeah, you do. So what you do with the auxiliary qubit or the spectator qubit is you're constantly measuring the off resonance on the spectator qubit, and hopefully because the spectator qubit is close to the data qubit, it would experience similar square wave noise. So if you measure you need to step up on the spectator qubit with the Jarrett-Mason ratio, you do a step up on a data qubit as well.
So in the actual setup, how do you fabricate this? How do you fabricate the donor? Sorry, the spectator qubit into the system?
They're two. I think they've done 2 qubit devices before.
Right.
And then with and you can identify the 2 different qubits by their splitting with the plunger bit, and you can also I think they can have like maybe 2 plunger, and if you have 2 plunger, you can I think it's been a long time.
Yeah, that's fine. And you think that the error is cyclic? Is that why you use a repeating square wave? Like cyclic over time? Is that why you use a square wave for your error?
Cyclic as in
it repeats?
Yeah. Well, not necessarily, but if but this is a simple model. I think we're looking at is to just again back to the the simple model of just an electron hopping left and right.
Right. Okay. So this is like the physical motivation why the error is cyclic because of this.
Yeah, kind of cyclic, I guess. I mean, if the tau RL is equals to tau LR.
I see it as like a try problem for error mitigation, not like because I think in real quantum devices maybe the error is not that cyclic, not like
no, because you're gonna have many.
It's like a try problem for error mitigation.
Yeah.
So if it's not cyclic, I mean, how could you really use like machine learning to train this live?
So in recurrent neural networks, it's basically used the previous data sets as well, all the previous data points, and it's kind of generating some dynamical system inside the model. And based on that, it learns the probability distribution of your noise.
Yeah, so like if the past data, so you need to make the assumption that the past data is going to be useful for like future.
Yes.
Yeah, so it has to be some sort of.
Let's say if the noise model is fixed, it's not changing with time, then you can use like normal neural networks in that case.
Yeah.
Just train it and then put it online. But if it's like changing with time, so based on the data or the noise model that you can predict before applying some machine learning model, then I think in that case, recurrent neural network will be good enough in that case because it's also for time series. And even like if the noise model is changing, but still it may not be changing very sharply. It's constantly changing with some step size.
Yeah.
So based on that, recurrent neural network has like it probably has like, let's say it has 2 outputs. Yeah. So one go back into the model and one go out to the for error correction. So that is going inside again. That basically creating some dynamical system inside the model.
Yeah. So at the very least, that should work better than this because this is sort of Markovian. Like it's pretty much trying to do error correction based on the current state. Whereas the machine learning will be non-Markovian. That should hopefully, if there's some sort of recurrentness or some sort of the future is based on what in the past.
Yes.
Then the machine learning should work better than this at the very least. This is state-based.
And on the cyclic side, the defects intrinsic to the device and the potential wells are not gonna move around, and I mean they're probably more prominent ones like closer to the ICT island or actually closer to the qubits, which are more dominant, and maybe because the traps don't move, and that could be kind of cyclic.
Yeah. So essentially you're saying that the error shouldn't change too much over time.
Yeah.
Okay. Yeah, which machine learning would be useful.
Yes.
Okay. Right, cool. That's it. Okay, who's up next?
I guess it's me.
Okay, you ready? You okay? Excellent.
Tracking the map.
All right, excellent. Thanks, guys. And
Thank you.
See you guys next week. Bye.
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 Oh yeah, I was nice to send slides to Kieran.
My presentation gonna be like similar with Seth, but yeah.
Pardon?
My work will be similar with Seth, like whatever he presents.
Oh, okay.
Yeah. We're working on kind of like same, so.
Well, back in the old days, like 100 years ago, when they taught in school, it's pure repetition, everything repetition. So these days, they don't do that anymore. They teach things once, they teach it. So when you go to uni, every topic you learn is taught once.